Welcome one and all. I thank the Honorary Secretary of Indian Association of Pediatric Surgeons for asking me to deliver a talk on this particular topic. I think he is actually testing my skills in keeping you all awake through this particular talk, and maybe also testing you to see whether you are going to sleep off during the talk, and I'll try my best to keep you awake. Now, I start with this slide. This is one of the documents which I have kept for more than 30 years. And this is basically my first ICMR grant for student research when I was a third year medical student. And they gave a grant of 250 rupees per month for 2 months. And I should thank Professor Thirumalai Kolandu Subramaniam, who was instrumental in installing that little fire of research and basic sciences in me, because he was the one who said that I could do this particular project in the Indian Medical Council of Research, and he also made sure that I presented the same as a third year student in the National Conference of Physicians of India. So that's where my journey to research started. And I will tell today the basic sciences, basic statistics, and how it can be not difficult as all of you might think. And I just want to break that myth that you can yourself do many of the statistics without the help of a statistician. So today we will see a bit about confidence intervals, sample size calculation, mean, median, students t-test, chi-square test, Fisher's exact test, odds ratio, relative risk, sensitivity, specificity, and then predictive values and ROC curve. That's quite a lot, but I will take you through illustrations so that you can understand it very quickly. Before you know what statistics you need to use, you have to find out what is the design of your study. And for a case report, you probably don't need much statistics. For case series, you're going to tell them all as a percentages. So all you need is a confidence interval. And the rest of the papers like cross-sectional studies, case control studies, or cohort studies and randomized control trials, these need at least some basic statistical knowledge to go further. So what is a confidence interval? So this is a paper we published in the year 2004. This is basically surgical risk factors for Hickman catheter sepsis. So the catheter-related sepsis was found in 9 out of 95%, which is 9%. So for that, you have to find a confidence interval. Confidence interval means based on your sample size, you can say, I can say this much confidence that the range is only between 8 to 22%. So for this, you need to use some of the calculators. Nowadays, a lot of calculators are available. I mean, quick calcs, med calcs, all the quick stats. I mean, all those things. You don't bother about the name, but at least know how you can work it out. And then you go to this graph pad, quick calcs, which I often use. And then you go, all these options are there. And then you go to categorical data and confidence interval of a proportion. And you enter these two details, 9 and 95, and then you will get a confidence interval. So how much confidence you can say that this particular proportion is what you will get again if you do the study. Now, categorical data are usually a percentage, like for example, infection versus no infection, success versus failure. It can be a continuous data like a serum levels, like serum creatine levels, serum C-reactive protein levels. And then the same thing can be normally distributed or not normally. For example, a blood pressure in a group of a population. So it can be low to high, but usually they stay around a middle value, which you can take it as a mean if it is normally distributed data. And you can use a parametric test like a student t-test for that. If something is not normally distributed, then you may have to use a median and an interquartile range, and then use a non-parametric test. So that is a normal distribution. That means most of the population fall in the middle of the range. Whereas if it is a skewed distribution, then that is called a not normally distributed, and then you need to use a non-parametric test. Now, you cannot plot all of them into a graph to see this kind of pattern. So there are tests to look at the normality of the distribution. For example, you have some 250 odd samples. You don't have to create a bar diagram. There are normality tests. I'm not going to do those, go into those details. But if you do those tests, then you will know which statistics to use. But you yourself may roughly know that, most of the patients are falling in the middle, the value. For example, you take a serum creatinine, most of them are falling around 1. Very few are high, very few are low. So you will know yourself. Sample size. Sample size is an important thing to know whether a particular study is going to be, giving a good good interpretation, good results which you can interpret. So for that, basically, let us examine this kind of example. You are comparing an open versus laparoscopic reimplantation or open versus lap pyeloplasty. If you are comparing only 10 patients on 12 patients on either side, your sample size is probably too low to look at any particular difference. So that is going to be not significant difference. Okay. So to look at sample size, you need to see what kind of study population you have. So this is again another clinical calculator. I just don't bother about the names, just to look at the principle. So you enter the details. See, for example, in group 1 and group 2, and that is the alpha and beta error. And then I again don't want to go into those details, but just look at how the numbers change. For example, this is a group where we want to this is a group where you have a difference, expected difference of 95% and 80%. So let us say that the success rate of laparoscopic reimplantation is 95% and then robotic reimplantation is 80%. So to show that 15% difference, you need to have this much a number of samples. So that's basically depending upon how wide the difference is. Now let us say that this number is little low. For example, it is not 95 and 85, but it is 95 and 90. So that is a smaller gap. Then the number changes to 868. So the smaller the difference between your expected groups, the bigger the sample size. Just that you have to be aware of. Now coming to mean and standard deviation, this is something which you should be easily able to find out with the help of an Excel. So you enter all the data, whatever like blood pressure or some serum value or whatever you are entering. So at the end of the cell, you put the cursor and then select the average, you get the mean. So that is very simple. All right. And then to get a standard deviation also, you go to more functions and then choose STDEV, and then you get a standard deviation in that end column. So you should be able to do all these things without the help of a statistician, which is what I want to stress. Now, comparing of the means, that is a student t-test. We feel that our data is normally distributed. So we want to compare the means. So you can enter the actual raw data and then compare it, which is the ideal way to do it. But the other way to do it is you find out the mean and standard deviation from the groups. So for example, this is a group A. They got 14 samples. They got a mean of 4.3 with a standard deviation of 2. And this is a group B, which is 12 patients. And then 7.5 is the mean and 5.7 is the standard deviation. And I've already shown that this is a normal distribution here. So you go to these calculators and then go to continuous data, because this is a continuous data here. Then t-test to compare two means. Then enter the values here. So you enter all these values, mean, standard deviation, and the samples size. And then you go saying that you check for comparison, p-value. And then it will come out with the results. And here it says the two-tailed p-value equals 0.05. So this is not significant at the moment. Anything 0.055 is not significant, but that is probably related to the sample size. Then if you have some 50 and 60 here, probably it will become significant. Okay. So student t-test is used to compare means, and this is one of the paper we published in 2010. So we want to compare the mean, value between before and after pyeloplasty. Here we want to compare mean H score in a hypospadias versus control. So here we wanted to compare mean shear wave velocity before and after pyeloplasty. So just remember, if you have a set of values, which is a continuous data, and you want to create a mean of that data, then compare those means, then using a student's data. Now, there is a different group of data where you have proportions. So as I said earlier, so you have a proportion. So I said that 9 out of 95 was the infection risk in that particular case study, which I showed earlier. So there we divided them into two groups where we used a non-touch technique and a manual technique. So here we are having a percentage. So the overall percentage was something like 10%. But when you use a no-touch technique, the infection was like 12%. And then when you use a manual technique, the infection was 6%. Okay. So this is the two groups where we have a proportion, not a mean. So this is a yes or no data. So that kind of data. So we put them into a 2x2 table. So we put here like 6 out of 47 means 6, 41, 47. Then 3 out of 45 is 3, 45, 48. So then the outcome is always on the top. You just have to remember this particular thing. So that is infection, no infection, right? So you go again to quick calculator, but this time instead of using the continuous data, you use the categorical data. So Fisher's or chi-square test and 2x2 contingency table, and then you enter your values, and then you say that go for test. So either chi-square or Fisher's exact test. If one value is less than 5, here it is less than 3, then you have to go for Fisher's exact test. So here the two-tailed p-value is 0.3, which is not significant. So in this particular study, we said that there is no big advantage of doing a no-touch technique because this is not causing a big reduction in the infection rate. So again, this is again a third slide, which is saying about which type of data to use for what test. So the quantitative data or qualitative data. So the quantitative data can be continuous, and then it can be nominal or ordinal. So nominal means, you have the yes or no data, or ordinal, like happy, neutral, unhappy, like that. So serum creatinine before and after PUV fulguration, that is going to be a mean. Okay. Whereas the same thing you can convert into different types. So the number of patients with the serum creatinine more than one. So here you're given a cutoff and then change them into, so you've defined what is your bad serum creatinine and then say that how many patients enter in that. So what has happened is here we are comparing the mean, which is like 3.2 versus 1.1. Whereas here you are comparing a proportion. So you're given a cutoff already. So the same study, you can actually change it into a different type of data. For that, you should already have an accepted definition of your splitting of the groups into two groups. If it is more than two groups, you can still do a 3-sample chi-square test, right? So that is a student t-test. This is a chi-square test. Now, the biggest question people ask me is when to use chi-square test, when to use odds ratio or risk ratio. So for that, you need to know what is a causation and what is an association. For example, in a hot weather, you feel like eating ice cream. So the number of people eating ice cream is definitely more during summer than winter. Similarly, the number of people getting a sunburn is also more during summer because they're exposed to the sun. So these two are causations. But you may also find that there's a correlation between sunburns and ice cream. So that is only an association. You cannot say that ice cream caused the sunburns. So this kind of understanding you should have to start off. So association versus causation. And if you think something is causing something else, then you call it a causation. Then there you can either do a odds ratio or a relative risk. So like, for example, cases versus control. Let us say that summer month are cases and winter months are controls. So you can say that the odds of getting a sunburn is more during a summer month. So here again, between odds ratio and relative risk, if the exposure has happened first, then you are looking. So you see all the subjects or the population in summer, then all the population in winter, then the exposure has already happened. Then you can say that the odds of sunburn in May versus December. On the other hand, you are looking at ice cream sales later on at the end of the year-end sales. There, the exposure has already happened. So you can say that there you can say that relative risk. So the ice cream sales, you can say that was more in May compared to December. Probably it was like 3 times more. So that is the relative risk kind of thing. Whereas when you are comparing two different groups which are totally unrelated proportions, for example, smokers in male versus smokers in female, sex cannot be a predisposing factor to smoking. So there is no causation here. So he can compare that by chi-square, saying that there's a significant increase in smoking among the males compared to females, right? So cohort study and case control study, I'm sure you might have learned about it. You already are using it all the time, but you probably have to know what is a cohort study. A cohort study is a prospective study where you have two groups which are exposed to either intervention A or intervention B, or a medicine A and a placebo, or a medicine and no medicine control, and then you look at the outcome. Whereas case control study is slightly different, where the outcome has already happened, and you can go to see whether that particular technique was used or whether that particular exposure is already there. So we looked at this F0 diuretic protocol is superior to F15 and F20 protocol. So this is a prospective study. So here it is a protocol and then the effect. So the usefulness of that. And whereas here in this particular study, we have looked at the outcome following diathermy versus cold knife ablation. So here we are looking at the stricture rate, but the technique has already happened. So that is a case control. All right. So when you are choosing the technique, when you are using cohort study, you are basically using a relative risk. And then when you're using a case control study, you tend to use odds ratio more. But both are similar almost. And I will tell you a little bit later about how they both can be, very similar. The odds ratio is basically a ratio of two odds, whereas relative risk is a ratio of two probabilities. Okay. So calculating the odds ratio, you again create a 2x2 table, disease versus no disease. Again, the outcome is always on the top, right? So you have the exposed and unexposed. Then you put them into four groups. So AD by BC. So odds of that a case was exposed, and then odds that a control was exposed, like that, and then you put that into this particular, that is the formula for odds ratio. So on the other hand, for relative risk, you find out the risk of the group in the exposed divided by the risk of the group among the non-exposed. So there you have that, you can say that this is this much more than this many percentage more than this. Okay. Now I come to this particular example. This is a common example which we used in our recent meta-analysis. So we compared robotic pyeloplasty and laparoscopic pyeloplasty. So here complication versus no complication, as I said, the outcome is on the top. So here complication, 28 complications out of 173, so that is 16%, right? Here 30 complications out of 323, that is 9%. So what test to use, whether to use chi-square or odds? You can say that they are two different groups. So we are only comparing two proportions which are not causing them. So you can still use a chi-square test to compare them. So if you do a chi-square, you are basically comparing 16% versus 9%, just that, nothing more. So your significance comes like 0.02, right? So that is also okay. But an odds ratio can be a method where you can say that what is the odds of a robotic pyeloplasty causing more complications. So for example, this is 9 and that is 16. So that is pretty much like double the complication. So doubling the complications, that is what this is. So you say that this is doubling the complication here, 1.88. So that is an odds ratio, which is again significance is the same. You work at relative risk, that is also same 1.7, which is pretty much close to 2, and also the significance is exactly the same. So you first understand that if the values are the same, your significance level is not going to change. Your odds or relative risk is also not going to change. But in this case, probably I will use a relative risk because here you are talking about the risk of robotic surgery causing more complications. I will tell you with even a simpler example. Now, before that, how you calculate this, here also we have this MedCalc where you put the numbers in exposed group, numbers in control group, and then you use that statistics to say test. Odds ratio calculator will give you the odds with the significance. Similarly, relative risk calculator will give the relative risk with that. Now, let us go to this particular example. Testicular tumor risk in gonadal dysgenesis. This is a common scenario. I mean, common scenario in the sense, common thing which we use. So what is the population risk of testicular tumor? So that is 2 out of 540, that is 0.4% from the various studies. In a patient with a gonadal dysgenesis, like a mixed gonadal dysgenesis or some of the XY DSD, the tumor risk is 24 out of 102. This is also from a study, that is 23%. So we straight away know that there is a 50-fold increase in the risk of them developing a gonadal dysgenesis. This is exactly what a relative risk says. So again, you put them into A, B, and C, D. So odds ratio is 63, whereas relative risk is 51. So that is exactly what we are saying. So there's a 50% increase in the risk of them developing a testicular tumor if they have a gonadal dysgenesis. So, and that is the significance value. So the significance becomes meaningless here because it is too significant, 50 times. So odds ratio and relative risk are very useful when it is close to 1. Like for example, if it is like less than 1, then you say that there is no association. But if it is more than 1, there is some association. More than 2, probably a very good association. But more than 50, it's very, very strong association. And the significance will be very, very significant here. So we all know by looking at it. So this is the usual example. Randomization tools, I'm not going into the details, but a lot of people are now wanting to do randomization study. So there are calculators to generate the random numbers for your samples. So if you want to make them to 2 samples A and B, you can always generate the random numbers using the randomization tool. So to summarize, if you have 2 groups and proportions, so you are going to do like a success or failure. You are going to use a chi-square test. If the minimum frequency is more than 5, or Fisher's exact test if the expected frequency is less than 5. If there are 2 groups like mean and median, it's a continuous data, you're going to do independent t-test if it is a normal sample, or a man-Whitney U test if it is a non-parametric sample. If there are more than 2 groups, then you have continuous data, then you can do one-way ANOVA or Kruskal Wallis test. You need SPSS software for these things, and that stage probably you will seek a help of a statistician. Now, testing the usefulness of a test. So here we have, just imagine that we have a particular serum marker where we want to see whether that is useful to identify a disease. So whether the disease are healthy, then the test marker becomes positive or negative. For example, C-reactive protein and severe sepsis. So here we have true positive, true false positive, false negative, true negative. So we can work out these sensitivity, specificity using all this formula 2x2 table, right? So ganglion cells absent in the appendix, and then present absence of Hirschsprung's disease. That is one. So ROC curve is a test to find out a cutoff for a diagnostic test. For example, you have a test where you have multiple values are being generated. Okay, so it's like a kidney function versus pyeloplasty outcome. So you have that kind of data. Like you want to look at a success or failure, and then you can say that what kidney function you can say is going to give you a success or failure like that. So for example, we did this study postnatal management of bilateral urotropelvic junction obstruction. So we wanted to see what kind of pelvis size or what kind of the GFR which we can predict that the opposite kidney will need a pyeloplasty. So these kind of numbers are best identified by an ROC curve. So we found that, if the opposite side has got more than 25 millimeter diameter, then probably they will need the pyeloplasty. And then if the opposite kidney GFR is less than 35, single kidney GFR, then probably that one will need a pyeloplasty. The opposite kidney I'm talking about in a bilateral PUJ. So here the area under the curve is something which tells about the accuracy of the test. So if the area under the curve is more, then probably the test has got a high sensitivity as well as specificity. Whereas if the curve is flat, like close to the diagonal line, then the test is not a good enough test. So making illustrations catchy and simple, I still like the bar diagrams much better. I mean, it looks very simple, but this is one of the bar diagrams which I often show. Like for example, it shows that if you use that pelvis size alone, then there's a gradual decrease over 1 year. To see the difference, you have to wait until 1 year. Whereas if you use a pelvis and the cortex as well as a form of ratio, you see a difference within 3 months itself. So you can see that this particular test is useful to predict an early success following a pyeloplasty. So that is a simple way to compare how the pelvis size alone works only at 1 year, whereas when you use the cortex also, then you can predict at 3 months itself that the pyeloplasty is working. So that is about the statistics. Now I'll go into the systematic reviews and meta-analysis. So what are the differences, how to start, then what are the various things we use in systematic review. Now why do we need systematic reviews and meta-analysis? So the evidence can be sometimes overwhelming. So for example, you go and look for whether particular data, for example, is the tip repair good for all distal hyperspadias? You start looking at one journal and then it says tip repair is a beautiful repair. But you look at the other journal, then that says that it is not. Then there are multiple journals, and then eventually you kind of get fed up because so many journals are saying yes and no and yes and no and again. So you are getting confused as to what is the actual truth. So, when we have a systematic review, then it is really useful. For example, this guy, Sile, did this particular systematic review and meta-analysis of the question I asked, is tip repair good for all distal hyperspadias? So he told that using an inlay graft during using primary repair decreases the risk of meatal stenosis. So he said that tip repair is not always good, and that is something which he has looked and then browsed through so many relevant articles, and then finally give us the summary. So that is how a systematic review is useful. So when you look at the hierarchy of evidence, the systematic reviews are pretty much on the top and meta-analysis are even above that. So basically, when you during your research career, you start with the case reports and case series, but slowly you have to go to cohort studies, which is a prospective study, and then randomized studies, and then you can go to systematic reviews and meta-analysis. So traditional reviews are subjective with unclear selection, broad question, methods are unclear, and you include all studies with various biases. Whereas systematic review has got a clear objective. So you have a selection protocol, you narrow the question, you define the methods about what exactly you want to look at it. So comprehensive search to get all studies, and then quality control and reduce the bias. You just make sure that you are not comparing apples and oranges, right? The systematic review is conducted according to clearly stated scientific research measures and is designed to minimize the bias and errors in traditional reviews. A meta-analysis, on the other hand, is use of a research tools to arrive at a statistical conclusion. So you develop a focused research question, define inclusion and exclusion criteria, search the literature, select the studies and assess the study quality, extract the data, analyze the and then present the results, then draw the conclusion. So we published this paper in 2021. So gender identity or gender dysphoria in patients with the disorders of sexual differentiation. We found that gender dysphoria is low if they are brought up as women in these conditions, whereas it is high in women who are brought up as women in these particular conditions. So this is kind of summarizing and giving us a guideline about what to do, what not to do. So formulating the review question, so PICO format. So what is the population? What is the intervention? What is the comparator? And what is the outcome? So that stands for PICO. So that model, which is used in RCT, is also useful. So I'll just give another example here. So we compared a proximal hyperspadias. This is another meta-analysis which we published in the year 2021. So what is our population? A population of proximal hyperspadias with severe CORD. So we defined what they are. Then what is the intervention? I mean, we divide the urethral plate, and then what they did. Then whether they did a single stage or two stage. And then what was the outcome? So complication. So even when we are analyzing these papers, so we have defined exactly what we are looking at it, and that is how we know that we have used this PRISMA approach, which is a preferred reporting items for systematic reviews and meta-analysis. So that is how we tell them that we looked at this many number of records and 102 records are identified. Then and that we are excluding this many records because they are either not recurrent hyperspadias or case series or some of those. And then we are also reviewing the duplicates, then excluding lack of full data, errors and reporting, review articles, commentaries. So finally we analyze the 26 articles. So there is a system. This is called a PRISMA flowchart, and we have to give this flowchart when we publish. So where to search? I mean, all the multiple databases are there. Then cross citations you have to check, and you have to carefully look for potentially eligible abstracts. So you look at the title, abstract, full text, and then it probably needs more than one reviewer to see that. If there are a disagreement between two reviewers, you go for a third reviewer, see whether you can actually include that particular article. And then the most difficult part comes, you extract the data. You extract the data you need. So what data you need to read this, how are you planning to look at the outcome? You will also have multiple heterogeneity. So variability in the participation interventions, then variability in study design, then variability in intervention effects, like that's called statistical heterogeneity. So heterogeneity is associated with the test called I2 statistics or Cochrane Q statistics. So if the difference is low, then you call it a low heterogeneity. That means all the papers you have included and studied are similar in nature, which is probably preferred. But it doesn't matter even if the heterogeneity is high, you just have to report that they have a high heterogeneity. So for example, here this is a systematic review and meta-analysis where we compare the laparoscopic versus robotic pyeloplasty in infants in 2021. So here, this is a forest plot. Forest plot is where we have a value of the in the middle. So this is the prevalence, which means the success rate. So the success rate is the overall success rate is given here, 97% for laparoscopic pyeloplasty and 94% for robotic pyeloplasty. So these are two different groups, but we are comparing this 97 and 94 here. So here the heterogeneity is low. That means they are all very similar. This all the values are lying very close to here. Okay, so that's what it means. And then the forest plot gives a very clear picture about where it is. So it actually gives a very good summary of all the articles you have compared. So bias, there are multiple kind of bias. I'm not going to tell, but you have to do a bias assessment, which what is called a traffic light plot. So each study is looked at carefully to see what kind of bias, whether the study population is clear, whether the type of procedure, whether the type of surgery, whether the type of follow-up, whether it is complete or incomplete. Some of them may be incomplete. You still may be able to include if only one factor is in red. But if multiple factors are in red, then you probably have to exclude those studies. Publication bias is inclusion of studies with only positive outcomes. This is a common thing which happens in the literature these days. So funnel plot is a plot to look at the publication bias, and if all articles are mostly within the funnel, then you know that they are all having minimal. Here one article is lying outside, but that's okay. But if all of them are all over the place, there is a lot of publication bias. Okay. There's also another plot called dot plot and for the same thing, publication bias. Then fixed effect, fixed effect, that the true effect of the study, same for random effect assume that is the study. So you have to see what. So in this particular paper, the fixed effect model, where they have assumed that the two types of pairs, right? So they have compared the odds ratio here, three different studies. So this is called a Tillman's odds ratio. Now, methodological concerns and quality appraisal of contemporary systematic reviews in 11. Here, the author said that only one review that year had a full survey. Only 33% described only 50% checked for heterogeneity, and only 3% are of good quality out of 17. So, are systematic reviews and meta-analysis the final answer? Let us look at it. There are so here these papers looked at whether caudal analgesia increases the rates of urethrocotaneous fistula formation in 2019, and they said that it does increase. Then there was another paper, 2019. Here they said that they said that caudal analgesia increases complication, but they said that it can be because of the bias. So there was the third thing which I read. It said that complications caudal analgesia, and they said that probably the other factors were more important. And then the fourth mechanical that caudal analgesia block is not influencing the outcomes of hyperspectral. So within 3 years, 4 meta-analyses have been done on the same subject, and then the pendulum has swung completely away. Now you might be concerned about it. I am not, because we all know that the evidence changes, and when the evidence changes and more evidence appear, and the evidence-based medicine also changes, so the meta-analysis outcomes also change. So this is the beauty of the modern medicine. We just don't believe that that particular herb or particular homeopathy medicine will work. We always look at it carefully, and if the evidence changes, then we also change our practice. So this is what a meta-analysis can be. We have to be aware that even meta-analysis are changing. So, but meta-analysis is helpful to prevent the overload of the information. So it summarizes the information into a concise capsule of information. However, inference depends on what information you have obtained and when. So it is likely to change with the type of information and with the time when you're actually analyzing. So that's about. Thank you for listening to this talk.